Hi there, my name is Paul Niujukian. I'm going to give you an overview of our new paper, Neuroelectrophysiology-Compatible Electrolytic Lesioning. In this work, we present a custom current source circuit for creating electrolytic lesions through chronically implanted intracortical multi-electrode probes. These probes are commonly used in both large and small animal neuroscience studies. Importantly, this technique does not compromise the ability to acquire neuroelectrophysiology subsequent to the lesioning, meaning that the electrodes and the rest of the probe is still intact for acquiring neural data, enabling for the first time the ability to record a neural population before and after lesioning and neural loss. We tested this with the Utah array in ex vivo sheep, in vivo anesthetized pigs, and in vivo macaques. We also tested a U probe in an ex vivo rabbit study to confirm that our technique works across multiple different types of probes and can be used, we believe, with any electrode that is capable of accessing passively to the underlying contacts. We validated our work using histology, current and voltage measurements of the active circuit undergoing lesioning, and spiking activity. I'm going to give you a brief overview of some select figures to give you a sense of this work. Figure 1 is the circuit diagram of the actual lesion circuit. The heart of this device is this Apex Technology PA97 op-amp, which was specifically chosen because it has a large voltage swing of hundreds of volts necessary to provide enough current to lesion and generate hundreds of microamps over the hundreds of kilo-ohm resistance that's experienced between adjacent and two electrodes that are two single unit electrodes in series. That's what's represented here by RL. The specific current that is dialed in can be tuned using these two potentiometers, RS and RB, over a large swing to give you the desired current to be lesioning with precisions down to the microamp level, which is necessary for this type of work. This circuit's fundamentally no different than that which would be taught in an undergraduate upper division analog electrical engineering circuits course, but the specific design considerations here of the specific op-amp and then the validation into biological tissue is the key insight and findings from this work. Figure 2 is our ex vivo testing in sheep, showing that we implanted Utah arrays into these ex vivo sheep brains and turned on the stimulator, dialing it in for hundreds of microamps at 10 minutes, and that resulted in this large cavitation that was seen here. When that specific current and time was dialed down, you got a much smaller dimple. And this very basic testing gave us confidence that the circuit was indeed performing as we expected, it was titratable, and it was appropriate for us to move to in vivo models. Figure 3 represents our in vivo anesthetized pig study, where we took a number of pigs and implanted them with Utah arrays and tuned and swept a number of parameters. Here was sort of the converged parameter of 150 microamps, which is what we ended up using for our in vivo macaques. And you can see this sort of cone-shaped area of lesion that is created through the circuitry. And zooming in here into the center of that cone shape into B, you can sort of see here pockets of health and pockets of injured neurons that is typical of this type of mixed injury environment. Contrast that to this region C over here, where there is virtually no injured tissue at all. This is all healthy-looking brain tissue. And this is giving us confidence that the lesion is indeed localized to the area of interest, and this sort of mixed environment of pockets of health and pockets of neural loss is what we term rarefied tissue and is quite similar to the type of injury border that's seen at the edges of an ischemic lesion that's very characteristic of, say, human stroke. We then took these findings and then moved to in vivo macaque studies. And I'm going to jump all the way to figure 7 here and end with this to give you an idea of the type of spiking neural analysis that was performed to validate that this technique not just worked in histology, but worked in an active awake brain. And these are two monkeys where the pre- and post-array spiking averages were looked at, and you can see that there's very little meaningful difference between the pre-array and the post-array. This is minutes after the lesion. The array is still capable of recording electrodes. And zooming in really closely here to these two black dots, these were the actual electrodes that were selected for the lesioning. And surprisingly, even they still have spiking activity that's being captured. So this, plus the subsequent analysis that I won't go over but in this brief discussion, gave us confidence that this technique is indeed performing lesions and generating neural loss while still allowing for the arrays and the multi-electrode probes to continue to record neural activity. For more details, I invite you to read through the paper, and I thank you for your time.